Hey guys, just checking the sound is working, and let's get into this. Right, so what's up, you scholars of enlightenment? So it's the day of NASA's OSIRIS-REX probe doing its daring high five, as the BBC puts it, with an asteroid, Bennu. So to run you through what's going on, an American spacecraft is about to attempt the audacious task of grabbing rock samples from an asteroid. So this is the OSIRIS-REX NASA probe. It's going to lower itself onto this 500-meter wide asteroid known as Bennu to make contact for no more than a few seconds. So the idea is that it wants to go take a sample of this asteroid Bennu to work out what were the conditions, what were the constituents of the very early solar system, the primordial solar system, that accretion disk that formed the planets. And the asteroids are a perfect ground for that, because this Bennu asteroid is what we call, if I can find it, I believe it's a carbonaceous or undifferentiated asteroid. So the constituents inside it have not really been changed. So if you have an asteroid which breaks off, comes towards the Earth, comes through the Earth's atmosphere, it gets melted, it changes the chemical composition of that asteroid. We don't know what its composition was in the very early solar system. With this object Bennu, if I can just look for control find carbonaceous. Here we go. The researchers understand that it is what we call a carbonaceous asteroid, meaning that its rocks still retain a hell of a lot of the chemistry that was present when the sun and the planets came into being more than 4.5 billion years ago. So there's a great desire to look at the composition of this thing, to understand what components there were in the early universe. And this is a really good way to get more information about what the conditions were like then and how planets formed. So this spaceship, the OSIRIS-REX probe, has been traveling to the asteroid belt between Mars and Jupiter, I believe, for around 4 years. It's got there, it's been there for several months, trying to work out somewhere suitable to land on this asteroid Bennu, which, if you have a look at the sizings given by the BBC article, is about 510 meters across. And it's found 2 places that it could land, which are a little bit dicey, but it was expected when the probe arrived that there would be a sandy surface. It would be able to go down and scoop up some samples. And it turns out that actually it's a little bit more difficult than that. So this probe has been there for quite a while, trying to work out places to land. So it was suggested that the asteroid would be a kind of sandy surface, but close-up imagery when the probe arrived has revealed that it's littered with boulders, and therefore we've had some time between the arrival of this probe at the asteroid trying to work out where it can land so it doesn't just smash into some rock and damage its instruments. So it's right there now around this Bennu. It's slated to do this high five with the surface and take a sample in the next hour or so. And what's essentially going to happen is it's going to fly in down to the surface of Bennu, this asteroid. It's going to touch the surface. It's going to deploy a probe, which we can get a nice little video of here in the Twitter article. Deploy a probe. It's going to spray some high-energy nitrogen, and a high-energy squirt of nitrogen into the surface, kick up some of the surface of Bennu, which will then get caught in this trap stay for a few seconds on the surface, retract with its sample, and then leave the surface with its sample intact and ready to be flown back to the Earth, ready to be analysed, ready for scientists to try to work out what the constituents of that asteroid are. So it might be that they have to do a second landing. There's 2 landing spots that have been highlighted in the preliminary research, but the idea would be that it goes down, takes the sample, and then will be ready to ferry it back to Earth so we can get, as I say, greater understanding of the primordial accretion disk and the components and conditions that went into creating rocky-like planets, because these asteroids are essentially the remnants that didn't go into creating rocky-like planets. We've looked at things like comets in the past. I believe it was the Stardust mission in 2003, looked at particles from the tail of a comet. Again, comets, these primordial leftovers from the early solar system, but in that case, probably from further out in the accretion disk because it's made of ice. And if the ice hasn't melted, it must be from further out, further away from the sun. So these are better, these asteroids are better for looking at rocky planets and what the conditions must have been like in areas similar to where planets like Mars, like the Earth, must have formed. So very, very interesting. I hope that this mission goes off without a hitch. And there's a live stream that we can actually get into and see what's going on. So NASA are running a live stream right now of this thing, and it's due to touch down.
I guess after that.
In an hour.
I guess after that, we are dealing with, actually the tag event itself. But
so everyone's in masks. Obviously, it's a very
in real time. That we have to wait
up-to-date current event.
The images take a lot of data to bring back to the bring back from the spacecraft to the Earth. And since we're on that low data rate, what we're using today is this real-time simulation that we've put together. So what we're seeing here, and we'll be referring to this throughout the broadcast tonight. This isn't any kind of real information.
I've never really seen the clear masks. I guess it's so you can tell they're talking.
So it'll let us know when key events are programmed to take place on the spacecraft and to be received back on Earth. There may be some lags in communication, but this is going to really help us visualize what's actually happening at asteroid Bennu.
So when will we expect those first images?
So everything's going to play out at this very low data
Just looking at the comments
broadcast today, and then the spacecraft has to back away from the asteroid surface. It has to cool off. It has to get back on its solar arrays, and then it's going to turn that high gain antenna to the Earth this evening. And we expect images to be coming in overnight, and we hope to have some great information for everybody by tomorrow.
I'm really looking forward to those images. People around the world are. So at this point, the space.
So it looks like the thing's going to go in,
and it's on
do its touch of the asteroid, collect its sample, come back out to a safe distance, and then beam a load of images back to the Earth, back to these scientists on the ground, to see if it's collected a suitable sample to then start its trip back to Earth. If that's not the case, there's a second site which has been scoped out, so we could have another zoom down to the surface and do another collection. But hopefully, fingers crossed, things will go off without a hitch tonight. They'll get the images back that they want of a suitable zoom down to the surface and a suitable sample collection, and this spacecraft will be on its way back to the Earth in the very near future. Now, it took 4 years to get there, so I'm imagining a similar time to get back, so we won't be seeing these images until about 2023. We won't be seeing being able to do any science on the composition and that sample till about 2023. But this is the very hard step, right? Getting there, getting down onto the asteroid, taking a sample, getting it back to Earth, and then doing the science in the lab is a little bit easier.
Would it have been feasible to have a robotic
Obviously, it's impossible to do any changes to the impact in real time because the light signals to go to the probe take a hell of a long time to get from the Earth to the asteroid belt, which is between Mars and Jupiter. I think it was about 18 minutes. Was it about 18 minutes?
That actually
It takes a
presents
while
other
anyway,
challenges of
so
its own.
there's no
For example,
time
if we
to
were
do
pick up a rock, it might actually
any
just crumble away, and we wouldn't actually get a
corrections if
sample out
things
of
are going wrong. So
Also, some of these
it'll
rocks
zoom
might
in,
actually be a
do the
bit too
collection,
stuck
come
to the
out, and
surface.
hopefully we'll see the
And if we
pictures
were to try to
afterwards
pry those loose,
that
they
show
might not
that
actually
everything
budge,
went
and we
well.
wouldn't actually even get a sample.
So let's have a listen to what they're saying.
These are all things that the team has to consider when designing something that's going to be operating millions upon millions of miles away from us here on Earth. So for now, back to you, Michelle.
Thanks, James. We'll be back to you more for later. Okay, now, I have been a Star Wars fan nearly all my life, and in one movie, Darth Vader said, rather famously, that asteroids do not concern me. But that is certainly not true for us this evening. We are all about
don't do
asteroids
the
here at the
puns and
Mission Support
jokes,
Area in
please.
Littleton, Colorado. And we are bringing you live coverage of our attempt to collect a sample from the asteroid Bennu. Now, OSIRIS-REX is a one-of-a-kind spacecraft with an extraordinary team of engineers and scientists charting unexplored places. It was launched on September 8th, 2016. The vehicle has traveled over 2.2 billion miles on a complex route to reach Bennu. It's scheduled to deliver its precious cargo back to Earth in 2023. So now let's take a closer look at OSIRIS-REX.
Over 200 million miles away from Earth, NASA's OSIRIS-REX spacecraft is preparing for an ambitious sample collection attempt at asteroid Bennu. Before it makes its approach to the rocky surface, let's take a look back at some of the incredible firsts for this mission, which almost seem like something out of a Hollywood movie. This is the first asteroid sample return mission for NASA, and it could be the largest return.
So this is the very first asteroid sample return mission. We've actually gone to an asteroid, sampled the surface, and then brought the sample back for analysis on the Earth.
It's first for the smallest ever body orbited, and it's second for the closest orbit of a spacecraft. This tight orbit has brought the spacecraft so close to Bennu that OSIRIS-REX's onboard cameras and laser altimeter have been able to image and characterize the asteroid's surface and shape better than Earth, our own moon, or any other celestial body. OSIRIS-REX has imaged Bennu down to 5 cm per pixel resolution, providing us with an unprecedented view into this rocky and boulder-filled world. With 28 onboard thrusters, OSIRIS-REX is one of the most maneuverable spacecrafts. This allows it to carefully and precisely descend to a spot on Bennu that is no larger than a few parking spaces. There have certainly been some unexpected twists along the way. However, OSIRIS-REX has capitalized on these moments. Right after arriving at the asteroid, OSIRIS-REX imaged rocky ejecta that has been bursting off Bennu. This is the first time we have been able to observe the entire life cycle of a natural satellite ejecting off an object, entering into orbit, and returning back to the surface. Because of Bennu's extremely rocky surface, the team needed to adapt the spacecraft's navigation method to an optical approach known as natural feature tracking, or NFT. This is the first time this approach
So
has been
Bennu's
used in
surface is
space,
very, very
and it will
rocky. We
allow
thought it would be sandy and
OSIRIS-REX
easy to
steer
come in and
itself
collect a
down
sample.
a sample from Bennu.
But there's a load of boulders on the surface, so it's
And
going to
now,
have to go in,
OSIRIS-REX is
firing
looking to set
rays at the
another
surface
first
to
for
avoid
NASA.
those boulders.
Successfully collect a sample of an asteroid and deliver it to Earth by 2023.
Very, very cool.
Welcome back. If you're just joining us, I'm Michelle Fowler from NASA's Goddard Space Flight Center, and with me is Dante Loretta from the University of Arizona. And you are here with us on a historic evening. It will be NASA's first sample return from an asteroid, the attempt to actually sample the asteroid Bennu. The spacecraft OSIRIS-REX is descending toward Bennu right now to take a sample and return it back to Earth. So Dante, let's talk more about this real-time simulation that we're looking at.
Yeah, it's been an exciting day already, Michelle. We're well over 3 hours into the tag sequence, which is the pre-programmed set of commands that are already on the spacecraft. Earlier, we departed our orbit around the asteroid, so we're flying over the sunlit side of the asteroid, taking images for the onboard guidance system called natural feature tracking. A couple other key events that have taken place already is the spacecraft has deployed its robotic TAG-SAM sampling arm, so the arm is ready, in position to collect that sample. And we've turned on and started collecting science data from one of our science instruments, the OTIS thermal emission spectrometer. The spacecraft has already moved into its second natural feature tracking attitude and is getting onboard positional updates as we speak. And I can tell you, everything is going exactly according to plan right now. It looks really good.
Oh, it's been an exciting day. So OSIRIS-REX has traveled more than 2.5 years as it navigated its way to this delicate orbit around Bennu. And once there, it began mapping the surface, one of the many tasks it and the engineering team have been conducting since it arrived. And there have been some challenges and surprises too, correct?
Absolutely. I can tell you already the science return from OSIRIS-REX has been phenomenal and rewritten a lot of things about what we know about asteroids. I'm going to talk really about 3 of some of the most interesting results for me. First off, we learned literally about 1 week after getting into orbit that Bennu is what we call an active asteroid. It is ejecting particles from its surface. These particles are coming off at relatively low velocities for the most part. They're actually going into orbit, spiraling around the asteroid, providing some excellent science, allowing us to map out the gravity field of this small body at an unprecedented detail, way beyond what we expected to do.
So these little bits flying off the surface, they go in predictable orbits, which we can predict with the theory of gravity, and we can help to plot the gravity and the composition of the asteroid with high detail.
Characterize their mineralogy. We were actually able to link them to another asteroid called Vesta, one of the largest asteroids in the solar system, and actually the target of NASA's Dawn spacecraft, which did a phenomenal job characterizing this target. And this just shows you that these asteroids are exchanging pieces back and forth as they collide into each other and shoot their particles off into space.
OSIRIS has processed its next image. Position uncertainty is 0.6 meters.
Wow. And I would say, back to the science, the final result that really is important from this mission is we did expect this asteroid to look sandy and beach-like. And that was based on the thermal properties as determined from telescopic observations from Earth. And we got there, and we used the OTIS and our OVIR spectrometer to map and produce a thermal inertia characterization of the entire surface. And everything turned itself upside down based on our models. The areas that we thought would be beach-like based on thermal properties turned out to be the largest boulders on the asteroid's surface. And the more fine-grained regions turned out to have what we call this higher thermal inertia, completely opposite of everything we expected, propagating a lot of great science as a result.
And so when you mentioned that there
So
are
nothing ever goes to plan. We thought we were going to get there. It was going to be a sandy, smooth surface, very easy to land on, very easy to take a sample. When you get there, it turns out it's covered in boulders, obviously more difficult to land on. But luckily, the probe has lots of sensors which allow it to navigate down to a spot on the asteroid to land, which is within a couple of parking spaces. So a little bit more difficult than expected. But hopefully, fingers crossed, it'll be able to land on that on a dime and collect that sample this evening in the next half an hour, 45 minutes or so.
To accomplish something that's honestly never been done before. And this is particularly challenging because Bennu has such a weak gravity field. So when you think about going into orbit around something, how do you orbit something where the gravity can't grab you and actually push you into orbit? It's all about flying the spacecraft. It's also very difficult to take a sample in a very low gravity environment. So thankfully, we have the mastermind behind the device that's going to take the sample tonight, Lockheed Martin's Bo Bierhaus. Welcome, Bo.
Thank you, Michelle. It's great to be here.
Okay, so let's talk a bit about why working in this low gravity environment makes it tough to get a sample, because you might think sort of at first you could just take like a robotic claw or a robotic arm and scoop something up, but that's not going to work in these conditions.
That's exactly right. The microgravity of Bennu provides a challenge of sampling that we don't normally face on Earth. You can imagine trying to use a shovel or a scoop on Earth, and the ground pushes against you, but the gravity keeps you on the ground. On Bennu, the surface gravity is thousands of times lower than on Earth, so if you pushed a shovel or a scoop into the ground, you'd push yourself right off the surface.
So you try to push a shovel into Bennu with the gravity being so low. You essentially bounce off and push yourself into space, so that's not a viable way of collecting a sample.
Landing a challenge, we wouldn't know how to grapple particularly well in this material. So we had to come up with a technique that worked in the microgravity environment and that could work in this tag architecture, this touch-and-go architecture of just a few seconds long.
Now, I understand you have brought some models with you, both of the spacecraft and of the instrument that will be taking the sample. So show us what you've got here.
That's exactly right. So this is a scale model of the spacecraft. The arm is extended in the sampling position. Partway down the arm, you can see 3 gas bottles. We'll use one of them today. This has high pressure nitrogen gas, which passes down the arm into the tag SAM head itself. And here I have actually a full-scale tag SAM. It's actually a device that we used for collection testing.
So you
on
can imagine
Earth.
the arm at the top
The gas comes
is the
down.
part
I
that's
don't have
going
the tubing
to
here
fire
show
into
you,
the
but
surface.
The gas comes down to the center of the tag SAM, is split into two, and passes underneath the head. There is now a high-pressure bubble of gas underneath the head that is mobilizing material, much like wind blows dirt on a dusty day on the Earth.
So it's
and we're surrounded
whizzing
by
up
the vacuum of
stuff
space.
from the surface of
So the
Bennu.
gas is, there's a high-pressure gas underneath tag SAM, and it will escape into the low-pressure environment of the vacuum of space surrounding it. And it does so through this screen around the entire perimeter of the tag SAM head itself. But while the gas can escape, the screen traps the material safely inside.
It's one of these sort of brilliant things about engineering.
So essentially,
is to have
the
things that are
arm
really,
comes
really
down onto the surface of Bennu,
easily. And so
squirts a high-pressure shot of nitrogen into the surface,
to provide
which
the pressure to collect the sample.
flips
That's
up,
exactly right.
throws
When we were
up a
first
load of
designing
dirt,
this
a load
device
of rock
many
from the
years ago,
surface.
we were thinking
The
we wanted
nitrogen
to
can then
keep it as
dissipate
simple
through
and
the
as
sides,
robust and as foolproof
but
as
a
possible.
screen
We
closes
didn't
and
want any
captures the
mechanisms, we
sample
didn't want
that's
any
thrown up
electrical
from the surface.
devices.
So the gas can
entire
escape,
collection is
but the
driven
sample
by the
can't, and
dynamics
it's
of the
collected.
gas itself. So once the gas
Very
is
clever.
released from the bottle and travels down the arm, the gas does all the work.
That's so cool. So what size particles are we talking about collecting here?
Well, tag SAM is designed to collect 2-centimeter particles, and I have some examples here to show you. So this is a 2-centimeter sphere. It's about the same diameter as a nickel. But of course, most geologic materials aren't actually perfect spheres. Most geologic materials are irregularly shaped.
OSIRIS has processed its next image.
Obviously can't collect things that are too big, because you'd have to fire a stronger and stronger jet of nitrogen. And
Excellent.
you don't want to fire something so hard that you
So we're
thrust
going where we
yourself
need to go
back
to
off
get
into
this
space.
material.
So you're going to get
most
a
geologic material
relatively
is
small
irregularly
samples, but
shaped. So this,
good enough for
rock
doing
is actually
composition
about 4
analysis.
centimeters long in its longest dimension, but we were still able to collect this in a test on Earth. And that's because even though it's 4 centimeters in this dimension, you can see that it's much less than 2 centimeters in that dimension, or even 2 centimeters in the other dimension. So while we're limited in one direction for 2 centimeters, as long as the other two directions are less, we can actually collect much larger particles into the tag SAM head itself.
Well, excellent. So I understand we have some animations queued up to give us a sense of what's going to happen on the asteroid tonight.
Sure thing. So what you're seeing
I
is the
find that
spacecraft
like the
descending at a
chirpiness
leisurely
really
10
off-putting. I know
centimeters per
that's
second to the
bad,
surface,
but it's like
15 times slower
the sort
than
of
walking
fake
speed.
chirpiness.
It contacts, the spacecraft senses contact and fires the gas. The gas mobilizes material underneath the tag SAM head. That gas escapes into the vacuum of space through the perimeter, and materials collected inside the tag SAM head. The spacecraft fires its thrusters and backs safely away from the surface of the asteroid.
Well, thank you for the tutorial, Bo. I mean, clearly the science community is going to be very excited to study whatever tag SAM collects. So thank you so much.
Thank you. It's
Hello
wonderful
to
be
everyone
here.
in the
Okay,
watch
speaking of
party in
all
the
of
comments.
important
If you have
tags
any
that we think is
questions,
happening in less than an
feel
hour,
free to shoot
right
them
now,
off.
Before we get any later, it would be a good time for us to get a tour of the Nerve Center here at Lockheed Martin Space in Littleton, Colorado. Right behind me is the Mission Support Area, or MSA, and that's where OSIRIS-REX team members are keeping an eye on the spacecraft right now. So let's send it over to Gary. What's going on, Gary?
I find the
So
clear
as I showed you
masks
earlier,
really
just around the
disconcerting
corner
as
from
well.
you,
I don't
this
know
is the
why.
heart of the tag
just odd.
operations, and we thought this would actually be a really good time to kind of check in with the team, see how things are going, and the best person to do that is joining me, and this is Sandy Friend. She's the OSIRIS-REX operations manager here at Lockheed Martin. So, Sandy, thanks for joining us. How's the team doing?
Oh, the team is great. We've been here on console since 6 o'clock this morning, sending the final commands, getting ready for tag.
Really cool. I know there's like 40 people on your overall flight team, but it seems like there's about 20 of them here right now. Maybe kind of give us a little idea of who some of these folks are and what they're doing.
Yeah, absolutely. So this is the amazing OREX team. You can see all of our subsystems here on console, monitoring their telemetry. Like you mentioned, we can't have everybody in here. We do have many team members supporting from other conference rooms in the building, and some even from home. So let's talk about a couple of the positions we have in the room.
That kind of sucks if you've been
corner over
working
there
on
is
this for
Dale Howe.
years and then
Dale
you have to
is our tag
help
phase
from
lead.
home.
You've been hearing his voice calling out events as they complete on board the spacecraft. Here in the center area, we have Curtis Miller. Curtis is our NFT lead. He is watching natural feature tracking, and that is how we are navigating to the surface of Bennu today. So he is watching how NFT is performing, how many features we're matching, and how that system is working.
So I know natural feature tracking, like you're saying, is kind of keeping an eye on telling us where we're going. And I know we're going to get into that a little bit later in the show. But also it's important just to stay in communications with the spacecraft. So what about comms?
Yeah, absolutely. So right behind me here is Sierra Gonzalez. She's our real-time operator, or our ACE. She is working with our Deep Space Network partners. Currently we're on a station in Goldstone and in Canberra, making sure we maintain our comm link. And our comm link is only 40 bits per second, so we're just bringing down that key information, but Sierra's here to make sure we keep that link going and our station operators informed. And right next to her is Estelle Church, and Estelle is our systems coordinator for this event. She's built all the command products that are executing. She's keeping an eye on how everything is progressing on board the spacecraft, talking to all of our subsystems here in the room, and making sure things are going just as planned.
Very good. I know you yourself have actually been on this project for quite a while, even back to development. I mean, how are you feeling tonight?
No, actually, I'm excited. I feel like we've done everything we can to make this successful, and I've been on this mission for 7 years, so I've watched it go from a spacecraft on paper to being built in our high bay to launch and everything here. And yeah, I'm excited. My kids were excited this morning, and we are ready.
Right on. That's so fantastic. So we're going to let you guys get back to it. I know
it is a really cool feeling to work on an experiment and see it from the theoretical stages to operation to results. This is like when I first started working at the LHC, it was just starting to come online. Then we started seeing first data. Then we started seeing results. Really cool to see it through from all of those steps. Feels a bit like your baby.
OSIRIS is slewing to the tag attitude, the third and final natural feature tracking attitude.
All right, so we're inching ever so closer down to the surface of Bennu. But today we also want to hear from you.
Masks, I just
so you can check in on live updates at our Twitter account at OSIRIS-REX, or using that hashtag to Bennu and back across social media to get in on the conversation. In the meantime, a question I had when I first started covering the mission is, how do you even begin to prepare for a mission of this scale? I mean, when I first heard about OSIRIS-REX, it really seemed like something out of a big budget movie. But this is a reality. We're actually going to be trying to sample on an asteroid. To put things into perspective for you, Bennu is about the size of the Empire State Building. That's really small for an object, and makes it exceptionally challenging for us to orbit something with such a weak gravity field. And that sample site we're going for today, Nightingale, it's just a few meters in width, which is about the size of a few parking spaces. So
you can't rely on the gravity of the object to give you the orbit. You have to do it yourself with a lot of thrusters, and the space probe has a hell of a lot of thrusters on board to be able to allow it to orbit. Maybe orbit's not the right word, but to go round this object and stay in the correct positions.
You're making your descent down to collect a sample. And on top of that, the team has actually programmed the spacecraft to steer itself down to the surface. It's truly incredible, this mission, and all the foresight that went into it. It really blows my mind. We actually have a couple questions coming in from Twitter, and a lot of people are actually asking about our fuel usage for the mission. This one question is asking, how does the craft have enough fuel to return back to Earth from the asteroid? So we're looking to bring that sample back in 2023, and OSIRIS-REX's thrusters are actually powered by hydrazine, which is stored in a container on the spacecraft. We're tapping into a little bit of that fuel today, on the order of maybe tens of grams, not a lot, because as you remember, Bennu has this microgravity environment, and it just requires a little bit of thrust to kick us in the right direction to collect a sample. That return trip back to Earth, that's a bit of a different story. We're going to be using a lot more fuel for that. But don't worry, the team has thought way ahead and has packed more than enough fuel to get us back here safely in 2023. But there's a lot more to come, and I'll check back in with you in just a minute. Back to you, Michelle.
Thank you, James. Okay, so let's take a quick look at the simulation to see where we are. As you notice with the simulation, the spacecraft has its arm extended now and is on a slow path toward the surface. So as we get closer to the moment of contact, the drama starts to happen in slow motion. And this is to maximize precision and minimize unintentional surprises. So, speaking of surprises, there is one big aspect of the OSIRIS-REX mission that's all about preparing for the unexpected. And joining us to discuss this is NASA Planetary Science Division Director, Lori Glaze. Now, Lori, you have kind of a dramatic specialty and a responsibility that comes with your position at NASA. You actually worry about things like planetary protection.
Yes. Planetary protection or planetary defense is sometimes what we call it, defending our planet from potential impacts. And Bennu is in a special class, and I think Dante spoke about this a little earlier.
So
that,
one of the questions
Bennu is actually a near-Earth
people have
object,
asked
or
is,
a NEO.
why don't we just look at
and a NEO,
asteroid
near-Earth
fragments,
object, is
bits
an
of
asteroid
asteroids
or a
that have
comet
come
that orbits
towards
sun,
the
much like our
Earth
planets
that have
do.
fallen onto
But
the
they're
Earth?
slightly unusual.
Well, that's because the composition and the nature of those asteroids is changed by their passage from the asteroid belt through our upper atmosphere by the intense heat.
So back to
and
NEOs.
that
Yes.
change
So
of
NEOs are
composition
somewhat
means that we
unusual
can't
in that
understand
their
what their
orbits bring
composition
them,
was
within the vicinity
in
of
the
Earth's
early
orbit.
solar system when the
technical
planets were being
definition of
formed. So
a
that's
NEO
no
is
good.
something that comes within
We
about
want
30
to see these
million miles
asteroids
of
in
Earth's
situ.
orbit.
We want to see these
And asteroids actually
primordial,
come close to the Earth
undifferentiated
all the
asteroids
time.
to be
One or
able to
two
see
per
what
week
the
actually
composition,
pass
what the
in between
conditions were
Earth
like
and the moon.
in the
But both
very
of those are
early
really
solar
small
system.
and not
So looking
dangerous.
at
But
asteroids that have
of a
chipped
much
off,
bigger
been
size,
sent
that could
towards
actually
the
be
Earth, have
damage to
landed on the
surface
Earth
if they were to
is
impact.
no good,
They can
unfortunately.
pass
We
by
have to
Earth
go out
closer than
there
the moon about once per
and
month.
get them
And
from
that's
the
why
asteroid
it's really
belt.
important for us to find them as early as possible so we can track their orbits, study their characteristics, and if necessary, we can mitigate a potential future impact threat. And that's where a mission that we're building now called the Double Asteroid Redirection Test, that's where DART comes in. And DART is going to launch in next summer, 2021, and it's going to test something we call the kinetic impactor technique. That could be used one day to help us mitigate a future potential impact threat by bumping an asteroid ever so slightly that's on a collision course with our planet into a slightly different orbit so it misses Earth.
Just a little bit is all you need.
Just a
So
tiny
DART's
bit.
really cool. Can we
But, I mean, that is
smash
really
into
exciting.
an
Now, I also
asteroid or an
understand that
object
not
with a
all of the
probe,
asteroids in the solar
change
system
its
are the same.
orbit,
There are
and
different
stop
sorts,
it
and NASA has some
impacting Earth?
upcoming missions to study these different kinds of asteroids. So tell us a bit more about that, please.
Absolutely. Yeah, we know that the majority of our asteroids are found in the main asteroid belt between Mars and Jupiter. And in fact, we have a mission that's going to launch in 2022. It's called Psyche. It's going to visit one of the biggest asteroids in the asteroid belt that's actually called 16 Psyche. And this mission is going to arrive in early 2026 and help us better understand if this asteroid is potentially actually the core of a planet-sized object. We also have other types of asteroids called Trojans that are clustered in two groups that lead and trail in Jupiter's orbit due to a balancing act of the pull of both Jupiter's and the Sun's gravity on them. NASA has a mission to those Trojan asteroids called Lucy. It's going to launch next fall, about a year from now, and it's going to go visit several of these Trojan asteroids.
So there's a hell
We
of a
have
lot
new
of
mission
asteroid-based
and we selected this
scientific
mission
experiments,
through our
scientific
Simplex
probes that are planned
small mission
for the next 10
program
years.
line. This mission is going to send actually two small spacecraft.
Maybe this
very small
explains why
spacecraft,
astronomy is
to
winning
two
all the Nobel
binary
Prizes at the
asteroid
moment.
systems and help us understand what it is that makes these binary asteroid systems different from one another. And so studying this full breadth of these diverse small worlds will continue to help us fill up the knowledge gaps of how our solar system actually formed and evolved over time.
So it seems with all these missions coming up, we're sort of in a golden age of asteroid exploration. But then there's this other aspect of the OSIRIS-REX mission, which is the sample return. And it turns out that we're also beginning this golden age of sample return to it, and not just to asteroids.
You're absolutely right. And we're really excited about all of these samples because they're so precious and there's so much science we can do with them. In addition to OSIRIS-REX, we're also partnering with the Japanese Space Agency on their mission called Hayabusa 2, which is actually already on its way back, bringing a sample from Ryugu. They're going to be coming back to Earth in December. We're also partnering with Japanese Space Agency on another mission of theirs that's going to return a sample from Phobos, which is one of the two moons of Mars.
For
And
anyone
then
who's played
finally,
Doom.
at the end of this decade, we're going to send a mission to Mars to retrieve the samples that are collected by the Perseverance rover, which is really truly our first astrobiology mission from NASA. And it's focused on looking for finding potential life, ancient life on Mars. So sample of return is really important because it allows us to study these pristine samples back here on Earth. We can then take advantage of our room-sized laboratories. All of this.
OREX off. OREX has begun moving the solar arrays to the Y-wing configuration to avoid possible contact with the surface during tag.
Great news. Moving right along.
So it
when
looks
you bring
like
samples
the
back, this allows us to use all of the laboratory
probe
capabilities
is
that
actually
we have
changing
here on Earth.
shape,
We can use the full
so that when
suite
it
of the
comes in
scientific
to
instruments
take
that
its
we have
sample
at
on
our
the
disposal
surface,
to help us
one of
better
its solar
understand the
arrays
sample,
doesn't
their
smash into
composition,
one
and
of
the
these
history of the
boulders.
body
So
from which they came.
it looks like it's changing
And
its
also
cross
having the
section,
samples back
changing
here
its
on
shape
Earth, allows
to
us
make it
preserve them
easier
for future
to
generations
collect a
to
sample.
come, and allows their future
so here it says
explorers to
move
analyze
solar
the
arrays to
samples
Y
using
wing. So it looks like it's
techniques,
changing
instruments
shape,
that haven't been invented, and to ask
narrowing
questions that
down
we
its
don't
cross
even know to
section
ask
so it
yet.
doesn't bash, essentially
That
bash
is
its
so
wing
cool.
mirror
Your life is all
on
about
one
how
of
we
these
navigate
boulders, doesn't
unknowns,
bash
and
one of
so
its
that's
solar
happening in real
arrays,
time around us tonight.
which I
But
guess
it's
it
reassuring
uses
to know
for
that there's an
additional
organized
power
plan that you're in charge of
on
to help take some
one
of
of
the
these
uncertainties out of at
boulders
least
that
one
is on the
category.
surface of this asteroid.
So, Lori Glees, thank you for joining us this evening. So good to see you.
Thank you so much for having me. I just want to add that it's been fantastic to watch the OSIRIS-REX mission so far, and I'm really, really excited for what's ahead tonight, and I want to say congratulations to the entire team.
Thank you so much.
Thank you.
Now, asteroids are not easily navigated. They're hard to see, they have low gravity fields, they're dark and rocky, and traveling around the solar system where everything is moving rarely means traveling in a straight line. Let's take a look at some of the big challenges the team has faced to get to this point.
As we started to approach
Alright,
Bennu
let's zoom up to the latest.
That's right. So we've got one more firing of thrusters with the spacecraft to get us lined up for the sample acquisition event. We call that the match point because what we're doing there currently as we're flying over the asteroid surface, in fact, it's the asteroid surface that's rotating underneath us. And when we fire thrusters for match point, we're doing that to match that rotational velocity so that the spacecraft becomes station keeping essentially
So it
over
doesn't
that
skip us
Nightingale
off.
sample site.
Absolutely. All right, so I think we have a little bit time now to turn to our social media desk. So, James, what's going on in social media?
Yeah, Michelle, it's super exciting. You just heard that checkpoint burn confirmed. We are now just very, very close down to the surface of Nightingale. And you guys have been really excited over on social media, too, at that hashtag to Bennu
So
and
we're
back.
getting ready to
Lots
go
of great
down to the
messages rolling in
surface.
here. Someone's really excited for our
So
little robot
one thing
friend
they
to
mentioned
go
there
rock
is that they
crunching on
have to do this
surface.
match
We had
point
someone
where
actually
the
attended our launch
velocity,
back
the
in,
sideways
taking an
velocity
apple,
of the
and
space
are now
probe
watching
has to
broadcast live
match
with us
the
today. Excited for this sample collection event.
spin, the
Yeah,
speed
Philip,
of
who kinda
spin of
puts
the
it in
planet,
perspective for us
of
here,
the
he said,
asteroid,
"This
excuse
is
me.
amazing and
And the
extremely
reason for that, you
difficult
can
in so
imagine
many
if the
ways.
asteroid is
Bennu's
spinning
orbit, spin,
quickly underneath,
inclination, the
and,
orbital
or
mechanics
you're
of this
going
long
too
mission
fast,
are just
you're going to
astounding.
skip off
I
the
can only imagine
surface.
how many orbit
Imagine
simulations
trying
have been
to
made here on Earth.
jump
It
onto
really
a
is
car
a
or
crazy
onto a
mission,
train.
and
If you're
we
not
also have our
matching
animal
speed
friends,
with
so
it,
that's- cheers
very,
us on
very
here as
difficult
well.
to do. You
Bennu
can
is
just
rough
skim off the
from,
surface. So they have to
just
fire
a couple of
thrusters
our pets here really
to match
excited.
that rotational
So,
speed.
we're now just
And
minutes
that'll be
away from that
easier
match point burn, and for
to
that, I'll take it
essentially
back to you,
punch
Michelle.
down into the surface,
Okay,
because
excellent.
compared
So,
to
you
you,
know, just a few
the
minutes
surface
ago,
is
Jonathan, you were
stationary,
saying
and
that
you
this
can
landing
punch
site
in,
is sort of a
collect
unique
something,
area on the
punch
asteroid.
out.
Tell us about this site.
Yeah, we spent an enormous amount of effort selecting the area on this asteroid surface where we wanted to get the sample from. And we kind of divided our analysis up into 4 different categories. First, we were looking at the deliverability. And this was a real challenge because, as we've seen earlier in the broadcast, the original guidance accuracy was 25-meter radius, and we're trying to get into an area that's 10% of that size. We have solved that problem with our amazing natural feature tracking solution, and as we've heard, that's worked really well, and it has updated its checkpoint and its match point maneuvers on board based on that information. That gets you down to the surface of the asteroid. So the next thing that we have to worry about is maintaining spacecraft safety. There's a lot of hazards on this asteroid surface, things that could damage a critical component, and we decided to focus safety on the things that were needed to get the sample back to the Earth. So there were certain things we could lose at this point in the
Okay,
mission
so they
if
don't
didn't
mind
fulfill that objective.
smashing the
We
spacecraft
still
to
have
pieces
some,
once they've
upcoming
collected the
major
sample,
milestones that help
as
us
long as
maintain
it can
that
make the
spacecraft
trip
safety.
back.
Now natural feature tracking is going to be switching over to calculating the contact point on the asteroid surface. And it has a piece of software on board called the hazard map. It's actually determining, is the location that I'm going to touch down on safe, a green area on that hazard map, or is it potentially hazardous, a red area on that hazard map? So as we get closer to the asteroid surface, a key moment is the 5-meter crossing. That's when the spacecraft makes that decision. Do I continue down to collect the sample, or do I back away and live to tag another day? After that, you've got down there, your spacecraft is safe. There's got to be something for you to pick up. Earlier in the broadcast, Bo Bierhaus showed us the size of particles that TagSam could actually collect. So we had to map the Nightingale area and other potential sample sites well below that 2-centimeter resolution. And in fact, we got 3.5 millimeters per pixel all over the Nightingale sample site. And we were really excited to see lots of particles of that size. And of course, the final parameter that we were looking at was the scientific value. And I can tell you the good news is any sample from Bennu is scientifically valuable. We've seen these hydrated clay minerals, we've seen organic molecules, carbon-bearing minerals all over the surface of the asteroid, exactly the kind of material that we're hoping to bring home.
So I understand the next big milestone we're looking for here is something called match point.
That's right.
So what happens at match point?
Match point is the final maneuver that the spacecraft performs by firing its thrusters. And that's where we become centered over the Nightingale sample site and begin that final descent down to the asteroid surface. And the spacecraft is solely focused on its safety calculation and the decision on whether or not it's going to proceed down to
So you're going around the asteroid at the same rate that it's spinning. So essentially you're just going up and down at this point, and there's no side-to-side component.
The spacecraft has to match the rotation of the asteroid so it comes directly down onto it.
That's right.
So how fast is Bennu rotating?
Bennu has a rotation period of 4.3 hours. So that's basically the length of the day on the asteroid. On Earth, the rotation period is 24 hours, which is why a day on Earth is 24 hours long. So that translates, because Bennu's a pretty small object, as we've seen, 500 meters, or about the same size as the Empire State Building. At the equator, the surface is moving at 10 centimeters per second. And it actually gets slower and slower as you go to higher latitudes. By the time you get to the North Pole, it's 0. Nightingale's pretty far north, so it's actually much lower than 10 centimeters per second. And that just kind of shows you the delicate precision nature of this mission. You know, we've got to get very low thrust maneuvers, very delicate, very slow approach to the asteroid surface. Everything kind of happens in slow motion when you're operating in a microgravity environment like Bennu.
So what's the next critical milestone after match point?
After match point, we're going to be looking for the natural feature tracking system coming back online, taking those images and additional correlations and precision on its knowledge of its position. And we might expect it to actually jump up. We've been hearing natural feature tracking uncertainties on the order of half a meter. It may go up a little bit as it goes through.
MSA on OREX Ops. OREX natural feature tracking system has resumed processing. Position uncertainty is 1.6 meters.
So you can see there we went back to 1.6 meters. That's because we went through the checkpoint maneuver. So whenever you impart a thrust like that, it adds uncertainty into the system. And we're seeing that with the natural feature tracking
1.6 meters in uncertainty in position seems quite big for something a couple of sizes of a parking space.
But Thomas, thank you for joining us.
So glad to be here.
I hope that goes down.
It's an exciting time, Thomas.
Happy birthday.
Thank you.
Yesterday,
That's right. Yesterday's his birthday. Yeah, that's right. Happy birthday. So, I guess, everybody here is aiming for this point in time called this tag SAM, but it turns out that there have been a lot of friends, a lot of colleagues that have helped get us to this moment. So, who's been along with us on this journey?
Well, look, I mean, there's a number of course, domestic partners, many of them around here. You talk to some of them, but there's also international partners, and the Canadian Space Agency provided the laser altimeter, which is an important instrument here. And of course, we have a partnership with JAXA. What we're going to do is actually share the samples from Ryugu, from Hayabusa 2, with OSIRIS-REX once it's back for maximum science. And that's really what international partnerships are about.
Maximum science.
So this is a big mission for NASA, but it turns out that there are many different kinds of partners in a mission like this. Give us a sense of the range of partners that we have.
Well, look, I mean, it starts with the University of Arizona. That's where the leadership is, and with you there and your entire team. But NASA Goddard Space Flight Center is a critical partner with managing, of course, especially also working with Lockheed Martin, who really, with that team deserves a lot of credit, and Kinetics, which was already introduced, as well as many others. If you really look, so often missions like that touch many, many states around the United States.
Absolutely. So, Thomas Zurbuchen, thank you for joining us, and we will see you later on in the program.
How do you feel, man?
I'm pretty excited. This is the final 10, 12 minutes here for contact. I feel really good. The team's in high
we're about
spirits.
10, 12 minutes away from contact. Very exciting time.
We have done everything possible to make this today a success.
Exactly right. And your mind is already out there, and the spacecraft is already on the way out in real time. Can you imagine that, right?
It's good actually to point out whatever has happened with TAG has already happened. We're well past that 18.5-minute one-way lag time.
So 18.5 minutes to get a signal out there. So we're past the point of no return. You're not going to be able to send a signal now and have it be detected by the space probe and to make any difference.
We know that we really have a sample.
That's a great question. We're not exactly sure what's going to happen right away. We'll know if we made contact with the asteroid surface today. We'll know if the gas bottle fired, and we know that we backed safely away from the asteroid. But we actually have a lot of work to do over the next week or so. We'll take a look at the images that we were acquired during contact with the asteroid surface, and then we'll go into a different imaging campaign. We're about 30 seconds from match point, so we're going to keep our ears open for that critical call out from Dale.
OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 1 meter.
All right, we're back down to a meter positional uncertainty. That's great news. So back to sample verification. We will, after we're well away from the asteroid and everything has kind of settled down, we have that robotic arm. We're actually going to use that to put the TAG SAM head into the field of view of SAMCAM. And we can look not only at the top of the sampler head like we're going to get with the images today, but we can actually turn it around and we can look at the base of TAG SAM. We have, in addition to the gas stimulation, we have contact pads. Simply by making contact with the asteroid surface, we think we can pick up fine-grained particles less than a millimeter or so. But basically, we're going to be looking for any evidence of asteroid material on or inside the TAG SAM.
Now, obviously, you don't want to go all the way
So
back.
they're going to collect the sample hopefully today, and then over the next week, the probe is going to continue to orbit Bennu, look inside its sample collector, see if it's got evidence of it having collected a suitable sample, and if so, it'll head back to Earth. If not, I guess it'll try and collect another sample next week.
Sample mass measurement. So what we're going to do is we're going to place the spacecraft arm out to the side of the spacecraft. So when it's in sampling configuration, it's actually pointed above. For this, we point it out in the other direction, and we kind of spin the entire spacecraft around. And we're measuring a property called the moment of inertia. We have actually already done this prior to initiating the TAG sequence today. So we know what that property is when the TAG SAM head is empty. Now we're going to be able to do it, hopefully, when it's full of asteroid regolith. So we're only looking for small differences in this property.
So they've spun round the probe without there being a sample inside. They measure the moment of inertia, and then after they've collected a sample, they're going to spin the probe again, measure the moment of inertia again, and if extra mass has been collected, if an extra sample has been collected, the moment of inertia between the two cases should change, and you know that you've picked up a sample. The problem here, of course, is if you pick up a sample and knock something off your space probe, which has the same mass, you won't get a change in mass. But you're hoping to see a change which is positive, and you've picked up some material and increased your moment of inertia, which is a measure of how difficult it is to rotate something. Something with a higher mass is more difficult to get rotated.
Yeah, thanks, Michelle. So you've been hearing those call-outs from Dale over the loudspeakers about those NFT images processing. It'd be awesome to actually grab a camera and make the trek out to Bennu to photograph it up close in person. But, you know, as we've mentioned, Bennu is a little bit far away from us right now, on the order of 200 million miles away.
200 million miles away.
Here's something OSIRIS-REX can deliver to you right now from the comfort of your own home. If you're on Instagram, you can head over to @NASA Solar System. We have 2 AR filters that you can use on your social media stories. This first one's called OSIRIS-REX and You and features OSIRIS-REX playing tag with Bennu around your head. The second one is called To Bennu and Back and allows you to place an asteroid wherever you are.
A little bit of a climb down from the hard science.
Bring an asteroid with you. So I understand we actually have a question coming in from Instagram from Mauricio, who asks, how do you manage the force back from touching down? I mean, the moment the spacecraft touches the surface, it should experience a similar force in the opposite direction. How do you manage that? Well, thanks, Mauricio. So the team actually thought ahead for this one when designing that sample arm. They actually added the spring-like mechanism to it that you can think of a bit like a pogo stick. If that sample arm were rigid, when contacting Bennu, it would stop its downward motion, and when firing the gas bottle to stir up a sample, we would just kick right back off into space, as Bo Beer has.
A little bit of buffering. Let's do a quick refresh, see if that cleans things up.
How do you manage that? Well, thanks, Mauricio. So the team actually thought ahead for this one. How do you manage that? Well, thanks, Mauricio. So the team actually thought ahead for this one when designing that sample arm. They actually added the spring-like mechanism to it that you can think of a bit like a pogo stick. If that sample arm were rigid, when contacting Bennu, it would stop its downward motion, and when firing the gas bottle to stir up a sample, we would just kick right back off into space, as Bo Beer has.
Interesting. A little bit of a problem with the live feed here.
How do you manage that? Well, thanks, Mauricio. So the team actually thought ahead for this one when designing that sample arm. They actually added
Looks
the
like people in the
spring-like
chat are
mechanism
going
to it.
crazy.
You can think of a
Looks
bit
like it
a
has
pogo
crashed.
stick. If that sample arm were rigid, when contacting Bennu, it would stop its downward motion, and when firing the gas bottle to stir up a sample, we would just kick right back off into space, as Bo Beer has.
So I guess we're going to have to sit and wait for the live stream to come back. See if there's another one that's working.
We're watching from Tucson, Arizona right now. They're watching from Tucson, Arizona right now. They've been really important to me. And another person who can't be with us here tonight, unfortunately, is my mentor, Dr. Michael Drake. He's the one who invited me onto this program in 2004 to be his deputy. I was a young, bright-eyed assistant professor. And we worked together for 7 years writing proposals to convince NASA that this was a program to fly for New Frontiers 3. We won the contract for OSIRIS-REX in May of 2011. And Mike passed away September, a real blow to the team. So
let's see if we can get this is somebody
today.
else's stream, so there's going to be talking over
real.
it. Let's
I mean, we're connected to our avatars that we put out there in the universe. So,
yeah, I know he'd be proud of us.
Yeah.
Memory, and we're going to start looking at those later tonight and have them available for everybody tomorrow morning. So this is just a simulation of the field of view of the SAMCAM, the sampling camera, part of our OCAM's camera suite. It has a clear shot of the TAG-SAM collector right in the middle of its field of view. You can actually see the lower end of the TAG-SAM arm here.
OREX MSA on OREX off. OREX is descending below 25 meters.
Okay, we're getting really close.
It's 25 meters from the surface.
It's the 5-meter crossing. Yeah. That's the really critical one. We're only a couple minutes away from that. So the spacecraft has one key decision left to make. It's calculating right now the probability that it's going to come down either on a hazardous area, as we defined on that hazard map, or in a safe area. So we may, at 5 meters, the spacecraft may decide that it's hazardous and it's going to back away, allowing us to live the tag another day. So to me, all my senses are on that call out right now.
Yeah.
I really want to hear that we are go for tag, so that's just a couple minutes away here.
And of course, remember that was planned for. That it has to know it's safe, otherwise it's going to back up and try again another time.
That's really how we solve the amazing challenges that this asteroid surface presented to us. You can see here that this is a pretty daunting terrain that we're coming down here. There's giant boulders all around the Nightingale site, even some large rocks inside the crater that we do not think the spacecraft would survive, at least with the ability to return back to Earth if it made contact. So it is there to protect itself first and foremost. Safety is always first, but we're feeling pretty good. Everything's gone really well today.
A couple of minutes away from that 5-meter safety crossing.
For a tag, but of course the spacecraft is the one that gets to make that decision.
It's just amazing. We've been rehearsing this event, all week long, all the different mission calls and milestones, but then to actually be here tonight and realize that this is going on 200 million miles away.
That's right, yeah. I'm pretty excited.
So, I mean, there were obviously a lot of firsts in this mission.
OREX MSA on OREX ops. OREX has processed its next message. Position uncertainty is 0.5 meters.
So the uncertainty is going down, which is good.
Offset is 1.7 meters. Hazard probability is 0%. Tag lateral velocity is 0.2 millimeters per second.
Oh my God.
Tag vertical velocity is 10.2 centimeters per second.
That sounded really good.
Yes.
So it sounds like the hazard map calculation looks really good.
So the probe has matched the spin speed of the asteroid very closely, so it's now coming straight down about 10 millimeters per second towards the surface, and it suggests that there's no chance of a hazard at the current time, so it looks like everything's still go.
everybody is laser focused on what this spacecraft's going to do. So I say let's let this play out. But those calls were really great. That was great news from Dale.
Yeah. Even more accurate than we'd hoped for in some cases.
Everybody seems happy.
Yeah. So I guess, there were obviously a lot of firsts in this mission, and there was a time when you said, a lot of what ifs basically. What if we could actually send a spacecraft to an asteroid? What if we really could bring back a sample of the solar system from billions of years ago? Did you remember where you were when those what if
OREX
questions?
MSA on OREX ops. OREX has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
So, it's happy to go down to the surface and take a sample. We're 1 minute away.
Touchdown declared.
All right.
Or less.
Sampling is in progress.
Less than a minute, so touchdown declared.
Oh my gosh, we're there, folks. That was amazing. I don't know if you saw the team here, but they just kind of blew up. They went from being steely-eyed to like celebrating the Super Bowl. So, it's all good. This is amazing. So congratulations, everybody. I know that Dante and Dr. Zabrukin are right here. And Dante, you somehow got over here pretty quick.
I sure did.
Congratulations. How you guys feeling?
Transcendental. I can't believe we actually pulled this off.
So the probe's touched down. It believes it's taken a sample. It's gone back
Please.
safely away from the surface, hopefully.
That's
And then over the next week, we'll find out if it has collected a decent sample and whether it can begin its long journey back to Earth by 2023 for the analysis of that sample and hopefully some insights into what that primordial early solar system was like.
It's almost hard to process everything that's happening right now. It's overwhelming pride in this team and everything we've done to get here. I couldn't really have anything better to say about this group of people.
All stations, this is systems. I can confirm that the backaway burn is
OREX MSA on OREX ops. Sample collection is complete and the backaway burn has executed.
So it's collected the sample, it's backing away. Looks like it's all gone super smoothly. Cool.
Dante, that was actually a really important call. We were celebrating on the tag, but that was actually probably even more important call. Why is that?
The pyro bottle's fired, so tag SAM operated. The backaway thruster's fired, so we're safely moving away from the asteroid surface. The spacecraft did everything it was supposed to do. So we did it. We tagged the surface of the asteroid, and it's up to Bennu now to see how the event went.
What does this mean to NASA?
This is the key milestone of this. Now it's a few days, right? To figure out how much we caught of this amazing sample that we're thinking about for decades. But I think this is just, I'm so proud of this team. Hey, team.
Oh, my goodness.
Oh, my goodness.
Well, I got to tell you, this has been a fantastic day, a fantastic journey. We're so proud of both of you for being here and supporting that team. We're going to get back over to the stage and Michelle, but some really good news. So back to you, Michelle. Thank you.
This is one of those moments we're all aware of COVID-19 because I want the hugs and the high fives and everything, but we're all going to keep each other safe. There are lots of super excited people all over who want to share in this moment and share their congratulations.
No kidding.
So let's take a moment to hear a few words from 3 institutional leaders who couldn't be here tonight, but they're cheering on the team on behalf of so many supporters.
Hi, everyone. Dennis Andrusik, Goddard Center Director. I am just so excited that OSIRIS-REX is collecting a sample from the surface of Bennu. The tag is just the pinnacle of the mission so far.
MSA on
Getting the
OREX
sample
ops.
back to Earth is obviously going to be the great event of the entire mission. But I got to congratulate Dante. You and your team, your project management skills as a PI, just superb. Rich, the operations team for getting us to where we are, and Lisa.
So it looks like everything went well. The space probe went down to the surface, matched speed, collected a sample, and has burned and backed away back into orbit. So over the next few days, It will do those moment of inertia calculations, see if it's picked up some mass, see if it's picked up a reasonable sample. If it has, it'll begin its long journey back to Earth. If it hasn't, it'll go down again and try again. So we'll have to find out what happens in the next couple of days. It's getting late here for me, guys, so I'm going to have to sign off. Really enjoyed watching that with you guys. If you have any questions, ask them now. Otherwise, I'm going to get off and I'm going to keep an eye on this over the next couple of days, see what the news says about it, and see if we can look forward to getting more insights into that early solar system and the conditions and compositions that led to the creation of Earth-like planets in the early solar system when that sample arrives back on Earth in 2023. Very, very cool mission. Very fun to watch. And I'm signing out. Night, guys.